And that is the antiderivative. I'm going to clean it up a little bit because these two can come together, can't they? That'll just become x squared plus 1. And we have a whole other part from the beginning that we never put in. Yes? I distributed the 1/2 through. I did the 1/2 here, and then I did the 1/2 there. So this 1/2 should be OK. Oh, it's no problem. OK, I forgot the first part. Don't tell me. Don't tell me. It was 1 over u squared, right? So, yeah. So negative. We had a 2 out there, 2 that we put in 1 over. Yeah, so we should be like 1 over 2x squared plus 1. Is that the antiderivative of the first one? I forgot the integral. It was 1/2 integral 1 over. Oh, no, it was 2x over x squared plus 1 squared dx. That was the integral from the beginning. So if we let u be x squared plus 1, this becomes 1 over u squared, which becomes u to negative 2. Antiderivative is negative u to negative 1. And then we had the 1/2 out here, right? So that should be it. 1/4? No, because this is 2x exactly. So the derivative of this is exactly this. We don't have to scale it. OK, so final answer. Final answer should be this. 1 over, or negative 1 over 2, x squared plus 1 in parentheses, then all this, plus 1/2 arctangent of x plus 1/2 of x over x squared plus 1 plus c. All right. Common where? Oh, yeah, we could put these together, too, couldn't we? Yeah, and then pull 1/2 out of everything. Yeah, we could do a little more. I'm happy with this. I'm going to stop. I actually want to see if we got it right. Well, I don't want to see if we got it right. I feel good that we got it right. I'm curious to see what Wolfram alpha will tell us the answer is. So integrate. What was it? X plus 1 over x squared plus 1, all of that to the 4th. Was it? Oh, it was squared. My bad. Squared. There it is. Yeah, you can't see it, but here we go. It's right. So that's Wolfram alpha's answer. Yep. They pull the 1/2 out of everything, and then if you put this and this together, the numerators become x minus 1. Denominator is the same, and arctan x. So good, we're there. I think it's a little easier just type it into Wolfram. But this again goes back to, why are we doing this? If we can go to Wolfram alpha and do this, right? Why are we doing it? Because anybody can do this. Anybody can do this. What we're trying to figure out is whether or not you have the capacity, the brain, to be able to follow this sort of problem through from beginning to end. Because that's what engineers, computer scientists, anyone in STEM fields, you have to be able to think, focus, right? I mean, it's not just typing in. This is, you could teach I could teach my daughter to type that in. It wouldn't mean she is a critical thinker. All right. What?
I don't like it.
You don't like it? Yeah.
No. Give me a week and maybe I will.
You have until next class. All right, so now we begin. Rational functions. So partial fraction decomposition. So a rational function is a ratio of two polynomial functions, right? So this is stuff we've seen back in college algebra. These are all examples of rational functions. Polynomial divided by polynomial, right? Cubic divided by linear. Quadratic divided by cubic. Fourth degree polynomial divided by cubic, quadratic divided by cubic, two quadratics, right? Ratios of polynomial functions are rational functions. What we're trying to establish right now is a procedure for integrating these types of functions, finding the antiderivatives, right? So there's a strategy for doing it. Here's the strategy. First thing you're going to do is you're going to take a look at the rational function and you're going to inspect the degree of the numerator and denominator, and you're going to compare them. You actually did that back in college algebra when you were trying to find the left and right hand behavior of rational functions. Do you remember that? Okay. So there's some good news. If the degree of the numerator is less than the degree of the denominator, we're going to just move on to the next step. So like in this first problem, we would not move on to the next step because this is bigger than this. This one, we would move on to the next step. This one, don't move on. This one, move on. This one, don't move on. If it has to be that the top is smaller than the bottom, okay? Top smaller than bottom, we proceed. If the top is not smaller, right? If the degree of the numerator is greater than or equal to the denominator, well, then we have to do long division first. Long division by hand, remember that? So for this problem, if we want to start this, we have to actually do long division before we even do any other thing. This one, we won't need long division. We will need long division. We won't need long division. We will need long division. All right? Okay, so that's the beginning of all integration of rational functions. Comparing degrees, determining if you need long division or not. Okay? Once you've got through that procedure, okay, you then, for the remaining rational function, you must use partial fraction decomposition to rewrite the expression. So now this goes back to the pre-cal. How much of this do you remember from pre-cal? Well, I could put the notes up here and I could just ask you to try and make sense out of this. But I think what makes more sense is for us to look at some examples and talk about how we do partial fraction decomposition. So I'm going to kind of step away from the notes here real quick. And I'm going to try and remind you of the way we do this. So this is no integrals. This is an algebra topic. If I have this expression right here, okay, I realize right now that if I were asking you to integrate that, you could do certain things. You could complete the square or something like that. But right now, if I'm asking you to do partial fraction decomposition, sorry, change this to a minus. My apologies. Change that to a minus. If we're back in pre-cal or college algebra and you're asked to do partial fraction decomposition, what you're being asked to do is to try and break this up into multiple terms. All right, not factoring, but kind of just partial fraction decomposition. So does anyone recall the steps for this? Factor the bottom. Start with that. Factor the bottom. So can you factor this bottom? Yes, x minus 5, x plus 1. Agreed? Okay. Once you're there, you have to look at those factors and you have to identify what type of factors they are. So this is a linear factor. Agreed? This is a linear factor. We have two linear factors, right? And they are distinct, which means they are not the same linear factor. Like this is x minus 5. This one is not x minus 5 also, right? These are distinct linear factors. So I'm going to write that down. This is two distinct linear factors. Yes? Two distinct linear factors. So the way that partial fraction decomposition worked at this point is that you said, okay, for each linear factor, I'm going to create a fraction. So I'm going to have two fractions I'm going to create from this. And the first one is going to be some number I don't know, okay, over x minus 5. And then the other one is going to be some number I don't know. I'm going to call it b over x plus 1. Does that look familiar to you all? Yeah. And then what you do is you try and figure out what a and b are. Right? Now, do you understand why this is actually really useful to us now? Because if you're trying to integrate this, right? Not so fun. If you're trying to integrate this, lots of fun, because these are simple, right? If you know what a is, it's just a constant over linear, right? The antiderivative of that's going to be basically natural log of x minus 5. You might have a constant out front, but easy to integrate, yes? Not easy to integrate, easy. That's the whole idea. So now, let's continue with the procedure. How do we find a and b? So does anyone remember how to find a and b now? I'm going to write it down here. Say again, how do you find a and b? How are we doing on time? Okay. I know it's been a whole, course ago, but how? How do I find a and b? Set something equal to something. I agree with that. How about we clear the fractions? We multiply both sides by the common denominator. What's the common denominator? That, right? Okay, multiply this side by that and this side by that. What would we get on the left side? 1, okay. 1 equals. Now, I'm only going to write it this one time because this is algebra. I will not write this every time. Right? That's what we're doing. Multiplying the left side by this, they cancel, you get 1. Right side by this, what happens when I distribute here to here? You're just left with the x plus 1 in the a, right? Okay, plus, when you multiply here to here, what do you have? b times x minus 5. Okay. Does that look familiar? At this point, right here, there are 2 ways to go about this. There's a shortcut, and there's the long way. The shortcut is obviously short, and it's nice, and when you can use it, you want to use it. The problem with the shortcut is it does not always work. So I'm going to just show both ways. All right? So here's the shortcut way first. Remember, our goal is to find a and b, right? Okay, so our goal is to find a and b. So the short way is you just look at these and you say, hey, if I want to know what a is, what I'm going to try and do is kill this off. So right here, I'm going to kind of play God. Can I say that? Can I say that or not? I don't know if I can say that. Okay, well, I can say it. Can I get in trouble, I guess is what I should be asking. I'm just going to let x be what I want it to be, okay? Let x be 5. Now, I chose 5 because that'll make that 0, right? So I have to replace all my x's with a 5. And do you see what it does? If x is 5, I get 1 equals a times what? 5 plus 1? So 6. And then that's just 1 equals 6a. So what's a? 1/6. Okay, I know what a is now, right? Okay, how do I get b? Do the same thing, but this time kill this one off. So you get to play God again. Let x be -1. -1. So that'll become 1 equals, this is gone, right? And then over here, b times -1 plus minus 5. So you get -6 over there, so you get basically b is -1/6. Right? So the partial fraction decomposition is what? 1/6 here? And over here, -1/6. And that's what partial fraction decomposition is all about. So again, if I wanted to integrate this, right? If I did, then I could integrate each of these. And so what I would do is I'd pull the 1/6 out and then just do a natural log on that. And then I'd pull the -1/6 out and just do a natural log there and I'd be done. Okay?
What do you mean by this way is not always working?
Well, I have to get to one of those. I'm not quite ready for that yet. This is the short way, though. I have to show the long way because we'll need the long way later. So I'm going to do the same, finish up this same thing. We're right here. Now I'm going to show you long. Yeah, the best way to show that the short way doesn't work is to give you an example where it doesn't. And you can pretty much see it right when it happens. You're like, yeah, I can't do that. Okay, so for the long way, what we do is we expand everything on the right side. Like we have to multiply this through. Okay, so let me do that. If I do that, I will get 1 equals ax plus a, and then plus bx minus 5b. Agreed? Okay, now what I'm going to do is I'm going to collect like terms together. So this is, I'm just going to rewrite first, ax plus bx plus a minus 5b. Now what we need is for these to be equal, right? The left side has to be equal to the right side. Now what I realize is that on the left side, this is really like 0x's plus 1, right? That's really what that is. And the reason I wrote that way is because if we have 0x's, that means these have to add up to be 0, don't they? And that means anything that doesn't have x in it has to add up to be what? What's left? 1, right? So watch, I'm going to write it again. Hold on. 0x plus 1 is equal to, check this out, a plus b x plus a minus 5b, like that. So all I did there was I factored an x out of these, right? But I factored out the back side instead of out the front side, which is fine, right? We normally factor it out the front, but I factored out the back for a reason. And I just put these two in parentheses. What I'm trying to get you to see is that if this left and right hand sides have to be the same, then the coefficient in front of x here must match the coefficient in front of x here, right? Those have to match. And then whatever number is here has to match with whatever is over here, right? For those two to be equal. So isn't this 2 equations then? And 2 unknowns? The system of equations. This has now become a plus b has to be 0. And the other one is that a minus 5b must be 1. And there's your system of equations. And how do you solve that? Well, either substitution or elimination. You have 2 options on this. So for this, I would probably, if I were the one doing the problem, I would probably multiply the top row by -1, make that negative, and then I would add straight down. And what happens if you add down? The a's cancel, you get what here? Negative 6b equals 1. And so b is negative 1/6. And once you know what b is, you can go back and plug in, you can get a. That's the long way. Long way, more powerful way though. This way basically will always work. All right.
So in the shortcut way though, it says that a is supposed to be 1/6.
Uh-huh.
If you plug in negative 1/6 into that equation that you had, what is it, a minus 5b equals, never mind.
You have to go back to your original
Yep.
order.
Yeah. You can go to any of them actually. It should work in any equation, but it'll work. Okay. So that's what you do, right? What I just did there was when we had 2 distinct linear factors. So what if you had 3 distinct, so let's say we start with a problem, it's like x minus 1, and on the bottom, let's say it's like x plus 5, x minus 1, x plus 4. What if we have that?
Don't you have like a bx plus cx or something?
We do add something, but not quite that. well, these are all linear, aren't they? So since they're all linear and they are distinct, they're all different from one another, then what I'll do is I will create now 3 fractions, right? And I'll do A over the first one, B over the second one, and C over the last one. And then I multiply both sides by the common denominator, and then I either do a shortcut or I do a long way, and I have to go find A, B, and C. I'm not working through that right now because it just take too long. We'll get to some practice as we do some problems, all right? I'm just trying to get you to remember the idea. For each distinct linear factor, let me say this again so that you'll really listen, because this is, I guess, the most critical part here. For each distinct linear factor, you will introduce on this side a constant over the linear factor. A constant over the linear factor. A constant over the linear. For each distinct one, constant over the linear, right? And we can integrate constant over linear. All right, so what if we had something like this? Now you have linear factor squared. So this is a repeated linear factor, and this one is a distinct, right? This is distinct from this. So you could say that these are distinct linear factors, but this one's repeated, yes? Distinct linear factors, but that one's repeated. So what am I going to need when I do partial fractions? What am I going to need for this linear factor? A over that, okay? And then plus, now, when you have a repeated one, how do we deal with a repeated linear? You do B over the linear factor plus C over the linear factor squared. That's how you do a repeated linear factor. So what if this had been, just for the sake of doing it, what if this number right here, instead of being a 2, had been a 5? You go B over x minus 1, C over x minus 1 squared, D over x minus 1 to the third, plus E over x minus 1 to the fourth, plus, I don't know where I am, F over x minus 1 to the fifth, and then you would stop. Question? Oh, shit. Sorry, make that a plus 1. Sorry, I was trying to get you to understand the concept, not even paying attention to the factor. Yeah, change these, please. Sorry about that. Change that to a plus 1, plus 1. Because, yeah, I would have canceled that a long time ago. Shit. Sorry about that. Thank you for catching that, because, yeah, that's kind of dumb.
Does that change anything? Because in the first example, it's just 1 in the numerator instead of...
That doesn't change anything. What's up top doesn't matter. I mean, it will matter in the answer. What I'm trying to do is get you to remember how we do partial fractions. We look at the denominator, we factor it, we say, do we have distinct or do we have distinct and repeated? For each distinct one, we just put, number over it, constant over it. If we have repeated, we have to just kind of build it up. We start constant over linear and then bring the power up until we get to the highest power. Okay? Okay, what if we have something like this? What if we have, I'm forgetting something here, hold on. Yeah, okay. So just to make sure you understand this, what if we had this? What would our partial fraction decomposition of that have to look like? Hold on. Chris Ochoa. Where's Chris?
A would be x
Okay. It would be what?
x, a over x,
A over x,
plus b over x minus 1,
x minus 1.
plus c over x minus 1 squared,
Yep.
and then d would be x plus 4,
Yep.
and then e will be x plus 4 squared.
Yep.
F would be x plus 4 cubed.
That would be the setup. And then you have to multiply through by the common denominator, clear your fractions out, and then you're solving for A, B, C, D, E, and F. That's almost, well, I don't know. For this one, we might be able to do the short way. But again, we'll get more practice with that once we get to it. Just want to make sure we understand how to do this. What if we had this? So this is, now we're going to change gears a little bit. What if we have, let's not make it that. Let's make it like x plus 3 over x squared plus 1. So what if we have an irreducible quadratic on the bottom? So I'm reminding you now. Okay, this is what you're saying. So anytime you have a quadratic down here that's irreducible, that can't be factored, instead of doing a constant over the constant over linear, if we have an irreducible quadratic, what we do is we put a linear expression over the quadratic. Linear over quadratic. Okay? What if we had this? Jace. So if we were asked to break that down using partial fractions.
Well, just to clarify, that
Yeah.
is its own problem, and that's not one big triple-decker fraction.
No. This is its own problem. Yeah. This is its own problem. This is its own problem. This is its own problem. So how would we do? What do you see here in the denominator? This is
X plus 1.
okay. So what type of factor is this? Linear, because what do we do? And this is quadratic, and it's repeated, and it's irreducible. How do I know that's irreducible? Because I know that that doesn't factor just by looking at it, right? Okay, so you have a linear factor, and you have a repeated quadratic, irreducible quadratic. So what do we do for the linear?
It'd be
A over x plus 1, and then what did we do for an irreducible quadratic in this one?
We put a
Linear over the quadratic. So this one is going to be repeated though. So how do you think we're going to have to do that then?
Just go BCD
Bx plus c, that's linear, over
over the quadratic.
quadratic.
Just repeat that.
And then I keep doing this and keep building up the powers. So see, how about dx plus e over x squared plus x plus 1. All that squared, right? And then plus,
You just continue to increase in your alphabet as you fly.
yeah, fg over x squared plus x plus 1 cubed. And that's where I'd stop, right? All right, so now that we've got that kind of out of the way, let me go back to the notes, and then maybe the notes will make a little more sense now. And then we're actually going to do, well, I don't know if we're going to do an example. We may not. This might be a good point for us to, well, we can at least talk about long division, I guess. Okay, so here's the notes. So here are the different cases. Let's say we have a denominator, like here's our numerator, some polynomial, who cares? Our denominator has 1, 2, 3, 4, 5, 6, 7, n distinct linear factors, right? These are all linear, ax plus b, but a1. So n distinct linear factors. Then for each linear factor, I have to put a over that, b over that, c over that, and stop at n. So why don't I use a, b, c here? Why are we using a subscript 1, a subscript 2? Why not use a, b, c? You might run out of letters, okay? Because if you had 52 distinct linear factors, you can't use a, b, c, right? And this is the way mathematicians get around it. We use subscripts. But the idea is still the same. Constant over the first linear factor, different constant over the second linear factor, and you keep doing that till you get to the last one. What if your denominator is linear factor repeated? Then you start putting your constant over the linear and then build up the powers until you stop at the highest power. Does this make more sense now that we've gone through it? Okay, what if you have an irreducible quadratic on the bottom? Well, then what you do is you put a linear expression on the top and then put the irreducible quadratic on the bottom. What if it's repeated? Well, then you build it up. What if the bottom is an irreducible, what if that right there is irreducible cubic? What do you think you put on top? A quadratic. So we don't go past this in this class. The biggest we go is quadratic on the bottom. But the idea is still the same. You can extend it. Like if the bottom is a cubic polynomial that you cannot factor, then we want to try and rewrite it with a quadratic on top. All right, let's see. I have 10 minutes. Let's do this problem. I think we can knock this one out. This one's pretty quick. By the way, there's nothing saying you can't do this a different way. Like, who knows? Maybe this can just go with a basic U sub. Right? Maybe this is just like U is x minus 1. Maybe it's not. But since we're in this section, we kind of need to see an example. This is our first one. Let's go ahead and do this. So assuming that no basic U sub works, no integration by parts, ultraviolet minus voodoo, assuming that's not going to work, no trig sub, let's go to our partial fraction decomposition. So the first thing we do, Jordan, the first thing we do when we're looking at a rational function is, where's Jordan? There you are, okay. I'm looking over here, I don't know why I'm looking. What's the first step? Yeah, check the powers. So the power on top is bigger than the bottom, which means we have to do long division. So long division is going to be first here. So on the side, I'm going to put x cubed plus 0x squared plus 0x. Oh, no, not 0x, plus x plus 0. And on the outside, x minus 1 like that. So I'm rewriting the numerator, x cubed plus x, and I'm making sure I account for any gaps that I have. Because with long division, this sort of thing pops up. We have to keep everything in order. And then we divide in. So this is where you sit here and you go, okay, what do I multiply x by? You just look at the x to get x cubed. So x squared. Okay, so I have to multiply by x squared, so I'll just put x squared here. And then you multiply x squared times each of those, so you get, what do you get? X cubed minus x squared. And then you have to subtract this row, which means all the signs change. This becomes minus, this becomes plus. And then you add straight down. What do you get when you add straight down here? X squared plus x, right? And now you play the same game. What do you have to multiply x by to get x squared? X. So you put x here, and then you multiply x times x is x squared, and then x times negative 1 is negative x. And then you come through and you subtract, which changes the signs. And what happens when you just get 2x here? And then you play the same game. What do I multiply x by to get 2x? 2. So you say plus 2. And you multiply 2 times x, you get 2x. And you multiply 2 times negative 1, you get negative 2. And then you come through and you subtract, so you change the signs again. And you add down. When do we stop? Geez, this seems like it could go on forever. When do we stop? Right now. When the power on this is bigger than this. Okay? So this is x to the first power. You don't have an x here. This is where we stop. So now we put plus 2 over x minus 1. So it's your remainder over the divisor. And so this is the long division.
You said to do when the thing outside the divisor. That, yes. Sorry.
This is the divisor.
The bottom part.
When the power there gets bigger than the leading piece here. See, so this one we were at 2x, right? The powers are the same, so I kept going. Over here we were at x squared, and then the power here is smaller. So, all right. So all this is saying, yes.
Quick question. How do
Yep.
you get x cubed plus 0x squared plus x?
That's just me realizing that I'm missing an x squared here,
Okay.
right? So in long division, we want to always allow ourselves a column for each of the powers. So I have a column for my x cubes, for my x squareds. If you don't have that in there, if you remember your experience with long division is when you don't leave those gaps in there like that, you can cause some issues. All right, so all we've done, right, is long division. That's it. That's the only thing we've done. So what we're saying is that this expression right here is equivalent to that expression, right? They're the same expressions. So this is just x squared plus x plus 2 over x minus 1. And that is good, right? We're very happy to see that, aren't we? Aren't we, Ricardo? Because how are you going to integrate that? Just quickly, right? I mean, this is not going to require partial fractions at all. All it required was long division. And now we can do them just term by term. So 1/3 x cubed plus 1/2 x squared plus 2x. I'll let you have the last piece, Ricardo. Plus 2 times natural log of x minus 1 plus c. Okay? So Ricardo looked at that. He's like, constant over linear. That's easy. Did the substitution basically in the head. Right? Okay, so that first one did not require any partial fractions. Just a little bit of long division. Let's see what the next one looks like. I don't know if I have time for it. Yeah, let's set it up. This one. Jacob? Where's Jacob? There you are, Jacob. Okay, on this next one, Jacob, are we going to use long division or not? To start the problem. Pardon? What are we checking for? We only use long division when what? The power on top is bigger than or equal to this one. And it's not. It's smaller, right? Since this is smaller than this, no long division is necessary. So then you go through and you're like, okay, maybe a basic U sub. Let's just try real quick. Would a basic U sub work? Hold on. U is 2x cubed plus 3x squared minus 2x. What's the derivative of that? 6x squared plus 6x minus 2 dx, like that. Do we have that up top?
Not yet.
Yeah, so you know how on the last one, the problems earlier, I was like, we don't have that, but let's make it happen. And it was like really kind of awesome how we did it. You can't quite do it when you have 3 terms like this. When you have a quadratic up there, it's not as easy. Because I would have to make that a 6x squared, wouldn't I? Yeah. Right? And so I'd have to multiply by 6 on top and bottom. But that would force the 2x to become a 12. Right? And I need it to be a 6. And I can't add and subtract. Trust me, it doesn't work as nicely.
Can you do it if you were to break them all up and then do an integration of each term?
You could, no, because you could do it on, like you could do those two together right there. No. I'm going to say no. Yeah. Okay, so this isn't going to work. So partial fractions. I have 1 minute. So I need to factor the denominator, right? So now I get to factor the denominator. And how would you factor that? Well, you would just factor, right? So x comes out of everything. And then how else does it factor? Yeah, if you just pull the x out, right, like this. Now, can you factor that? Or is it irreducible? Is that irreducible? that work? 2x squared plus 4x minus x minus 2. That's factor. So this becomes 2x minus 1. 2x plus 2. So what do we have on the bottom? 3 distinct linear factors. And so we are going to be able to use our partial fractions to figure out how this breaks up. And then we'll come back and do the integral. That's where we'll leave it. Technically, there's no homework for this section yet because we haven't actually gotten into the problems yet. We spent the whole class pretty much preparing ourselves for it. And that's why I like to spend 2 days on this, because the first part's just making sure we're ready, and then now we'll start going into the problems. So I would say tonight's homework would be a good chance for you to just go back, review some things, get yourself up to speed with the other stuff, make sure you feel good about it, and then come back next time and we'll finish up. All right, everyone, have a good day. Let me turn this off. Oh, yeah. And then, hold on a second. Let me turn this off. Oh, shit. Someone hit it. Someone moved it.
I think it was just now, though.
Oh, was it just? Oh, did you? No?
I don't think it was the whole time.
Really? Okay, good.